All right, so today we are going to talk about eigenvalues and singular value decomposition. But this is a 3 week lecture that we are going to complete. Then by the time we finish with the third week, we'll now have full understanding of PCA, okay, principal component analysis. And Godwin, you suggested next week's practical is going to be, or next week's lab is going to be a practical scenario where we'll pick real world data and we apply all the things that we have learned. But we are not going to use any machine learning model. We'll use, as I said, we're going to use NumPy, Matplotlib, these things that are used to mathematically build models. That is what we are going to use. So that is what is going to happen next week. Okay, so make sure you don't miss it. Charlotte, please, if you can send a message on the platform, inform them that we have started. Okay. Okay. So now any square matrix possesses a collection of one or more distinguished scalars called eigenvalues. Any square matrix. So the term over here is a square matrix. That is something that you have to take note of. Any square matrix possesses a collection of one or more distinguished scalars called eigenvalues, each with it associated or distinguished vector known as what? Eigenvalues. So we have your eigenvectors. We have the eigenvalue. Then the eigenvalue is having associated vector called eigenvector. One, it has to be a square matrix. And when you find your eigenvalues, we can determine what the eigenvectors. When a matrix acts on a vector, we call it transformation. So the matrix is transforming the vector. Remember, we saw this formula AX is equal to B, right? So we are doing the transformation here. We are transforming the X to B using this transformation, which is the A. Right. So when a matrix acts on a vector via matrix multiplication, the eigenvector specify one, the direction of pure scaling, and the eigenvalue also specify the extent. So there are terms that we are going to use over here, such as stretching and shrinking. Stretching or shrinking. Okay. The eigenvector determines the direction. And if no vectors, we say they have what magnitude and what direction. So the vector is going to determine the direction. Then the eigenvalue is going to tell us the extent to which this vector will be shrinked or to be stretched. Okay, will be shrunk, sorry, and also will be stretched. Okay. So the eigenvalues, what they do is that they scale it. So the scaling can be shrinking or what? Stretching, right? So eigenvalues and eigenvectors are of fundamental importance. And its application is not only in machine learning, but you find it also in dynamic systems, both continuous and discrete statistics, and all sort of things. All right. In engineering, you use a lot. So I'm not surprised that you are seeing its application in machine learning and also data analysis. So anyone here, if you want to move into data analysis, these are things that you should not, gloss over. You should master, right? So remember, the eigenvector or the eigenvalue has it associated eigenvector. The eigenvector determines the direction, which the eigenvalue is the one that scale it. The scaling can be stretching or shrinking. All right. So let's define this. Now let A be a square matrix. I'm stressing again, the A should be a square matrix. That's the first thing. So let A be a square matrix, and you have a scalar. And this scalar is called the eigenvalue of A. If there is non-zero vector, we'll find out. Now, when you look at this equation, the only time, okay, we have two solutions for this. The first one is when you have your V is equal to 0. This is trivial. Trivial solutions, they are not important to us. Okay, all trivial solutions, they don't have any significance, right? So when v is equal to 0, that's a trivial solution. Put it somewhere. That is not what you're interested in. All right. So if A is a square matrix and we have a scalar called eigenvalue, and the vector v should not be equal to 0, then that means that vector can be called eigenvector, such that when that vector that we are talking about, which is the eigenvector, is transformed, that vector is transformed, we are going to get the same vector, but it will be scaled. Let me take it again. When the eigenvector, the vector that we are interested in, is transformed, we get the same vector. Somebody said it will land on the same vector, or to be on the same vector space, but it will be scaled. So if, let's assume I have a value over here, let's say 3 over here, and I apply a matrix to this 3. According to this rule, this 3 is supposed to be equal to 3, but is going to be scaled. And the scaling is a scalar over there. So it can be 2 over here. All right. So A transform 3 to the same 3, but is being scaled by 2. So the scaling, it can stretch it or it can also shrink it. If it is less than, I think less than 1, right, it will shrink it. Okay, if it is more than 1, it will scale it, or it will stretch it rather. Let me use that word instead. All right. So that is that for the eigenvalue and the eigenvector over here from this explanation here. So this is the scaling factor. This is the scaling. This vector is the same as this vector, right? This vector is the same as this vector, and this is the transformation, the matrix during the transformation. Right. So in geometric terms or in geometric interpretation, what we are talking about is that the matrix A, okay, scales or stretches the eigenvector by an amount specified by the what? By the eigenvalue. So what the transformation is doing is that it is stretching it, all right? It is stretching the vector by some amount, and that amount is specified by the eigenvalue. So when A acts on that vector, okay, you end up getting a scaled version of the same vector. And that scaled version is determined by the eigenvalue. So the eigenvalue is the one that tell us how much it is scaled or how much it shrunk. An eigenvector is a vector that, when transformed by a vector, only gets stretched or shrunk by a certain amount, but does not get rotated. An eigenvector is a vector that, when you transform it by a vector, it only gets stretched or shrunk by a certain amount, but do not get rotated. Do not get rotated. Okay. Hey, are you okay? Any question?
Does that mean
Yes.
eigen eigenvectors are not transformed by matrices, just vectors?
Come again, Albert.
Yeah, I'm asking that, is it that
Mm.
for eigenvectors they are not transformed by matrices, they are transformed by vectors, or
Oh,
the
no, no,
terms
no,
are
no.
used?
No, no, this, sorry. It's supposed to be a matrix. Okay, thank you for,
Okay.
yeah, it's supposed to be a matrix. Sorry, it's a typo. Right. It's a matrix, please forgive me. So when eigenvector is transformed by a matrix, okay, so it only gets stretched or shrunk, because that is what we said over here. That in geometric term, the matrix A scale, okay, stretches the eigenvector by a certain amount. Right? It's a typo error, please. I'll correct it before I share the slides. Let me correct it right now. All right. So it's done by the matrix, not the vector, because it's the matrix that is doing the transformation. So once it transforms it, it has to get it to a different vector, but this time it's getting it to the same vector. It's getting into the same vector. And once you get to the same vector, it's going to be like a linear combination, right? So it is the same vector multiplied by some scalar, and that scalar is the eigenvalue. Okay, so thank you. It's matrix, not a vector. All right. So let's look at this. Now take your pen and paper because you're going to do some calculations over here, and I'll ask you guys to do it for me. So let's look at this chart, the first one, this chart. Now we have our basis, which we have the I and the J. Then with this I and J, we have a transformation. So if you look at this transformation, let's pick the I star here. See the transformation here, which negative 5, 4. Then if you look at the J star, those are 2, 1, right? So this is our transformations. And we already know this, that if you have a transformation, when we apply it to the basis, okay, so if you want to transform this vector, we have a vector over here, which this v, all right, which is equal to negative 3, all right, negative 3, okay. So if you want to apply the transformation to this, it's simply we are applying this transformation to the individual basis, right, and multiply it by our vector. Okay, that is what we learned last time. All right, so this part correspond to this, then this one also correspond to that. All right. Now, when we perform the transformation, this is what we are getting. But now we have a straight line. Now, if you look at this line that you can see, it is in the same direction as the vector, right? The same direction. I'm not able to draw it perfectly, but in the same direction as the vector. Now, if you look at it, it is spanning, or it has a span, a list of vectors. If you look at the V here, we have V1, we have V2, we have V3. Look at V1. If you look at V1, what is the dimension? Sorry, what is the coordinate, or what is the vector? It is minus 2, right? Minus 2, minus 2. Now let's look at V2. So this is V1. So V2 is also negative 1, negative 1. Negative 1, negative 1, right? Now let's look at V3. So V3 is also equal to 4, 4, right? Yes. All right. So when we take our vector minus 3, as you can see over here, when we have this, this is a line or a straight line, and on this straight line, we have a set of vectors. So we say the span, okay? So we can have a lot, we can have a lot. So if you look at it, you see that it's not always, or we are not going to get only negative 3, negative 3. We can get what? A span of this, a lot of them. Okay, a lot of them. That is what we are talking about with regard to our eigenvector and also the eigenvalue. Okay, so when we do the transformation, we get to the same vector, but it's going to be a linear combination. It's going to be a scalar multiplication of that vector, right? So scalar multiplication of that vector. So we can span, it can be negative, it can also be positive. Okay, if we take that line and try to find all the vectors that can be found on that line, all the vectors that can be found on that line. Right. So some history about eigenvalue and eigenvector. So it's a hybrid German English term that we use. Okay, and it has come to stay in mathematics. It has come to stay. Something that, I mean, it plays crucial role in all engineering applications and also other areas, even in physics, right? So when we have our equation, this is this equation, you've seen it, okay? How do we, I mean, solve? How are we going to calculate this eigenvalue and also eigenvector? How are we going to solve it? Let's go through this process. So this is our equation, you've seen it, where we transform a vector by a matrix to the same vector but be multiplied by a scalar, and that scalar is the eigenvalue. Now you know this I, right? That is what an identity matrix. An identity matrix multiplied by any matrix is the same thing. Okay, so it's not going to change anything. So we just put it over there. What we can do with group terms, when you group terms, we can factor the v out. So when you factor the v out, we have this equation. But there are two ways to solve this. I made mention of one. The first one is when what? The v is equal to 0. When v is equal to 0, we'll get this to be 0. And that is a trivial solution. It has no significant implication. So with that one, we throw it somewhere. Then the next one is how do we determine it? We don't want the v to be 0. The v should be non-zero. So how do we solve it? Then we have to pay attention to this part. This part. So the second one, as I said, is when v is not equal to 0. All right. Now, this is a homogeneous linear system, okay, and it's having what? Non-zero solution if and only if each coefficient matrix, okay, is what? Singular. Is singular. Now, this is something that we have to understand, okay, here. When we say a singular matrix, okay, what are we talking about? Any of you can go on and tell us. I want to explain something here to make sure that we understand. When you say a singular matrix, what are we talking about? Any of you can go on and tell me. Please unmute yourself. Let's be quick. Oh, hello guys. Let's be quick.
That
Hello.
means that the inverse
Yes.
does not exist.
Okay, the inverse doesn't exist. All right. So, but I want a proper term for it. When you say non-singular, the inverse doesn't
So
exist.
it's a square matrix that does not have any
Yes, it doesn't have any inverse, but there's a term that I'm looking for. The determinant is what?
The determinant is zero.
Yeah,
That
the
is, it's not
determinant.
invertible.
Okay, so the determinant is 0. Now, there's something that, although we said we don't want the determinant to be 0, but here we need the determinant to be 0 in order to solve the equation. That is something is a little bit strange over here. That's why I wanted you guys to contribute so that you understand it. Now we said when you have this equation, all right, this equation, we have two solutions. The first one is when we said the v is equal to 0. We don't want that. But the other one is the v should not be equal to 0. But how do we solve this equation? How do you solve this equation? We, as I said, we can pay attention or we pay attention to this part, this version of it. Now remember what this is going to, or the final answer will be in the form of what? A matrix, right? Or it's a matrix multiplied by some scalar, sorry, a matrix subtracted by some scalar and you are multiplying the scalar by the identity matrix. So you end up getting a matrix and you're going to multiply the vector. So what we can do is if this is a singular matrix, we'll find a way to be able to determine our V. And that is a key observation that is used in solving eigenvector equation. That is a key observation that is used in solving eigenvector vector equation. Okay, we want this to go back to 0. That means when you find the determinant, it's supposed to be 0. Once the determinant is equal to 0, it will help us be able to determine the v. Okay. All right. So now when we say a matrix is singular, or a matrix is singular if and only if it has what? 0 eigenvalue. Okay, 0 eigenvalue. So let's look at this example. So we have a matrix over here. This is a 2 by 2 matrix. We have it entries. We'll come back to this definition later on. Now, this is what I said. So this part you already, this is an identity uh, matrix and you already know it. So here becomes 1, then 0, 0, 1, right? So that is why if you multiply it by the scalar, you end up getting the lambda 0, 0, lambda, right? You get this. So when you do the subtraction, this is what you get. Okay, this is what you get. Now we said it is singular. If it is singular, it means once we find the determinant, it is supposed to be equal to 0. We can equate it to 0 once we find a determinant. We need to do this so that we can be able to solve the equation. And once we equate it to 0, we've gotten a polynomial of whatever dimension that you are dealing with. This is of second a square polynomial, right? Which is of dimension 2. All right. So for this is a quadratic, something that we all can do, but to find out or we see how it is done. All right. So you see why we said we want this part to what to be singular so that we're able to determine that. If it's not singular, it will be difficult. So once this, a result matrix is singular, it can be equated to 0, then we will be able to determine our eigenvalue. Okay. Now we said if you solve this equation and you get the eigenvalue to be 0, then it's telling you that that matrix is what? Is singular.
Sir,
Yes, Albert.
so I wanted to ask, is it the matrix A that has to be singular, or like when we do A minus lambda times the identity matrix, that must have a determinant of 0?
It is this one, the result
The
time.
expression here,
Yes, this expression that has to be 0.
that must be singular, right? Not
Yeah, yes,
necessarily the matrix A.
yes, yes. It's not the A, but it's this expression that has to be singular so that we can
Okay,
find the eigenvalue.
okay.
So once you solve this expression and you determine, you find out that your eigenvalue is 0, then it informs you that that matrix is singular. I hope it's clear. So once,
Yes, yes.
so once you get that expression, but after solving, you realize that the eigenvalue is 0, then that matrix A, or the matrix that, the matrix that you were using, okay, it becomes singular, or it is singular because you had the eigenvalue to be 0. All right. Okay, so once you have this equation, it's quadratic and we can solve it. Okay, so that is quadratic equation or the formula. Now, when you solve this, how many solutions will you get when you solve this equation? How many types of equation or how many equations will you have? Okay, Albert said 2, Joshua 2. Okay, you get 2. All right. I think let me put the question well. I'm not looking for the answer, but uh, based on the determinant, the discriminant here, let me use the word, based on the discriminant here, okay, how many solutions will you get out based on the discriminant? You are supposed you will get two solutions, but let me use the word type. Yeah, let me use the word type. Okay. So based on discriminant here, how many type of solutions will you have? Based on the discriminant, how many type of solutions will you have? You get two answers, which is correct. Okay, so based on this discriminant, how many? Okay, yes. Albert said real and imaginary. Godwin said, okay, Joshua said three. So you're going to get three possible solutions based on this discriminant. You're going to get three possible solutions. The first one is what? The first one is real, right? Where they are different. So when it is real, that means x1, okay, is not equal to x2, right? Then the other one is repeated, where x1, okay, is equal to x2. Then the next one is when it's complex, where you have, let's say, x plus some complex value I, then y. Okay, so you are getting a complex. Right. So you are going to get three possible solutions out of this. Okay. But our focus is solely going to be on real. Okay, for now, on real for now. This we are introducing you guys. So those of you who pick it up, you can go deep and find out. All right. So based on these discriminants, when the discriminant is greater than zero, okay, then we say that the lambda one is different from the lambda two. That means two distinct eigenvalues. When the discriminant is equal to zero, then we have a repeated value or a single value. That is where the eigenvalue one is equal to the eigenvalue two. Then when the discriminant is less than zero, that is where we have what? Complex conjugate, which we are not dealing with that. So our focus now is the first one, where the eigenvalue one is not equal to the eigenvalue two. All right. All right, so let's look at this. So we saw this matrix earlier on. All right, then we have our equation. So this is uh, the equation when you complete this expression, which is a, okay, minus our lambda I. All right, so this is what we have, and then we put it to zero. So when we solve this, we're going to find the determinant of this. So when you find the determinant of this, okay, we equate it to zero, then you get this quadratic equation. When you solve it, then we have uh, 3 and 1. So the eigenvalue, we have 3 and also negative 1. 3 and negative 1. All right. Now that we have our eigenvalue 3 and negative 1, the next thing is to determine the vectors. So let's take the first one. When the eigenvalue is equal to 3, what is the vector? All right, so when eigenvalue is equal to 3, we go back and do substitution. So we go back here, so we replace this with negative with 3, sorry, also replace this also with 3. All right. Oh, no, it's negative 3 rather. Wow. Please do the calculation for me. Let me confirm whether it's 3 or negative 3. Do this calculation for me right now. It's negative 3. Okay, thank you. So it's negative 3, not 3. All right, so let me change this right now in the slides. So, okay. All right, so negative 3 and negative 1. All right, so here we do the substitution and we'll get this matrix out. We get this matrix out. Okay, so we've gotten a matrix. We'll talk about this matrix later on. Now, this is another matrix that we've gotten. We'll use it in our eigen decomposition. Right. So we apply this matrix to our vector that we are looking for because we said that it is A minus the lambda I, which is our identity matrix, all multiplied by our Venn. So once we simplify this, okay, we can now multiply it by our vector, and then we can equate it to 0. So once you can find the determinant of this. When you find the determinant of this, can you confirm this is equal to 0? Can you confirm the determinants of what I've circled is equal to 0? Yes, we can do that, right? So that means it agrees to what we said, that this expression, when you pick this expression, determinant is what? Is singular. Okay, that means it is true. All right. So now, when you have this means that we either have or no solution or a lot of them, right? Either you have no solution or a lot of them. That means when you have a line, thank God. If you have a line, it means you have what? It's going to have a lot of combinations. Okay, that's linear combination of that vector. But we don't want this. We prefer the second one, which is a lot of them. And that is what we use to determine our eigenvector. Right. So we do multiplication and we will get this thing out. Now, if you look at V1 is equal to V2, so automatically, I mean, V1 will be 1, then V2 also will be to be also 1, right? So when we have this eigenvector, I mean the eigenvalue which is -3, its eigenvector is what? Is 1, right? Okay. So let's look at this. So you see that on this line, okay, on this line we can get our 1 1 here. Sorry, let's go here. We can get our 1 1. Yes, we can get our 1 1 here. Now if you should write this, can get a 1 1 here, all right, which is still on it, spanning the same line. Okay, so if you should write, this is what I wanted. So if you write this equation, which is a v is equal to some lambda, okay, v. Now our matrix is -5, all right, -4. Then we have our 2, then 1, right? Then our uh, eigenvector, uh, which one were you even using? I'm coming, a minute, a minute, a minute. Okay, so this is what we are looking for. Please multiply the -1 by this. Let me see whether we get the -3 by 3. Multiply this one for me. Multiply this. Let's see. Because this we can be expressed. Yeah, I think it's true. They are supposed to get, but I mean, find out. Is it 1 or -1? I don't know. Multiply this whether we will get this. Because this expression is supposed to give us this A vector. A will multiply the vector. Then we have the -3. That is also going to multiply the same vector again, right? So, I mean, here we can factor. It's 3, 3, right? Then here's supposed to be 1, 1. I made a mistake. It's not supposed to be negative. It's supposed to be 1, 1. Okay, so I have to change it. Why? So change it to 1, 1. Let's see. Why am I making a lot of mistakes today like that? Change it to 1, 1 for me. It's not supposed to be -1. It's supposed to be 1, 1. Okay, so it is 1, 1. All right, so that's correct. So here is supposed to be 1, 1. All right, so it's trying to tell you that this vector, okay, uh, is okay. So we had the eigenvalue to be what? -3, right? Yeah, we had the eigenvalue to be -3. Yes, we had the eigenvalue to be -3. Okay, so it's supposed to be -3. Then we have 1, 1 here. Okay, that's the implication. So what he's saying is that if this matrix transform this, we are going to get the same thing, but I mean being multiplied by some scalar over there, which is -3. So here, if you bring the -3 out, okay, we'll get our 1, 1 here, as we saw for this. Okay, so the -3 and this. Okay. Now the next one is when it is equal to -1. Okay, so we go to the same process. Now here, this is a little bit different, but let me take my time to explain it so that you guys understand the concept here. Now let's try to do this thing together. So once you do the expansion, you end up getting -4, right? Then 1 plus 2 V2, right? 2V2, okay, is equal to 0, right? So you get -4 then 1 is equal to minus 2 v2, right? All right. So here, one of them is going to be the free value or the free, yeah, the free value, and it's going to be v1 because you're going to have this will cancel that. So we have 2 v1, right, is equal to v2, right? Okay, so I mean the free value is the v1 because if the v1 is equal to 1, we'll know v2, right? Okay, so if we should create our value, then it's going to be 1, 2, right? 1, 2. Okay, so this now please put this one down. The Put this value down. Okay, we will use it to prove a concept. So 1, 2. Now, when you look at this, it's the same thing. You remember when you draw your plane, okay, you have your straight line like this. Okay, we can have the span. Okay, we can have a lot of them there. So if you look at it carefully, who can tell me the relationship between these two? The relationship between these two. You can type it between these two. Okay, so Gordon said 2v. All right, so if you look at this, yes, you just have to multiply and you be able to obtain that. So you multiply uh, this by 2 or you have this one. Okay, you have this or you multiply this one by 2. So it's the same thing. That tells you that it's going to be somewhere on this. Okay, so if I can write this v using a lot of, I mean, scalars in front of it. Okay, so some of them will stretch it, others also will shrink it. All right, so that is what is, I mean, happening somewhere here. Okay, so you saw uh, our vector, which is 1, half, and 1. Okay, so we are using it on the matrix and we'll get this at the end. All right, so what do you think? So if we go and check our eigenvalue, which is -1, so just a matter of, I mean, bringing -1 out and cleaning this, right? So it's telling you that this matrix is transforming this to the same matrix, but is what it's doing is multiplying by what? A negative value. It's multiplied by a negative value. Okay. I hope it is clear. All right. All right. So we have some examples over here. I don't want us to waste time. So maybe can you try the first one for me? Then the number two, you guys can do it when I share the slides. So I'm giving you guys 5 minutes. Can you try the first one for me? You find the eigenvalues and eigenvector for this. 5 minutes. Let's be quick. Okay. So I'll create a poll, then you get the eigenvalue. So lambda 1, lambda 2, v1, and v2. So start work. Corey, please type it in the poll, eh? Type your answer in the poll. Godwin, type your answer in the poll, eh? All right, so let's see. Precious, Iman, Joshua, Godwin. All right, the rest of you, please try, make sure you do it. Okay, so I'll publish the results and you see. So they all had it correct. So the lambda 1, lambda 2, 2, 4. Then the eigenvector negative 1, 1, then 1, 1. So let me publish the results. You see the solution. All right. Okay. Yeah. All right. So please make sure you practice. Okay. Okay. So make sure you practice. Okay, the second one. All right. So this is what I was trying to explain. That this is like we picking from A. Then the vector here, we are getting the same vector, but there's a scalar that we use to what? That stretch it or to shrink it. Right. So this is the explanation I was given over here. So we are doing the same, we are doing the transformation to the same vector, but what is going to happen to that vector is either it will be stretched or it will be shrunk. Okay, so now we are done with that. We are going to an important application known as eigen decomposition. But before we get to that, we have to understand it came by or um, how it is proved. All right. So we have these things and we have to understand where we are getting these values from. Okay. Now, if you look at this, the A, which is the P, okay, this one, it is the column of the eigenvector. So if you take the vein 1, you remember the vein 1 we had 1, 1, right? So that one is the first one. And the V2, remember we had, I asked you to put, what value I asked you to write? It was 1, 2, right? Okay, 1, 2. All right. But you can also use this. All right. So we can also use the half one. We also saw that. Okay. So that is that for the P. Then this is a diagonal vector. We've done diagonal vectors. Diagonal vectors, the diagonal, they have entries. Apart from that, any other entry is zero. All right, so this is the diagonal vector. Now, if you look at this diagonal vector, you will see that it's also equal to the eigenvalue, -3, -1. So remember the eigenvalue, the lambda 1, we had -3. Then the lambda 2, we also had what? Uh, -1, right? So this is it. Then this, no, okay, so this is also the same thing because this is P over here. All right, so it's the same thing. Now we are trying to come out with a formula or a proof. So what we do, we can multiply the P by its inverse. The multiply. So once you do it to Kofi, do the same thing to Amma. So if you multiply this side by the inverse of P, then we need to do the same thing over here. So the inverse of this P will go to I, which is identity, and we can eliminate that. We don't need it, right? But this side, look at what we are getting over here. Okay, so there's a matrix, and that matrix is equal to the inverse, sorry, the inverse and the matrix and another value over here. We are going to define all these three things and find out the role that they play, okay, in our decomposition. All right. So we say that a square matrix A is complete if and only if there exists a singular matrix P and a diagonal matrix, this, okay, diagonal matrix such that when we multiply this, you can get this, or when you multiply this, you can get this. If you look at it. So now when you multiply the inverse, the a matrix and the inverse by the matrix that we're interested in, we'll get a diagonal vector, or we can have a matrix which is also equal to a matrix and multiply by inverse and a diagonal vector. Now, what is this P and P inverse? We will define that. So take note, it's not any ordinary matrix, but we'll learn how to define it. And that is what I was trying to explain to you here. You see, the P, we get the P from the eigenvector. The P is gotten from the eigenvector. So the P that we are seeing over here, that is the vector formed from the column of the eigenvector. So if you do your calculation, the eigenvector that you will get, you use it to form the matrix for the P. So once you know the P, you can find the inverse of the P. Now, how do you get a diagonal vector? The diagonal vector is gotten from the eigenvalue. The eigenvalue. The diagonal vector is getting from the eigenvalue. Why is this thing important? We'll find out. Let's proceed. All right. So now once we know these matrices, which is our P and the P inverse and the diagonal vector, we can also find something that is very, very important, known as the trace. Okay, the trace of a vector. What is the trace of a vector? The trace of a vector is when you sum the diagonal, okay, the entries of the diagonal, that is equal to the trace of a vector. So anytime you have a diagonal vector, okay, you want to find each trace. Okay, so we have a practical example. So one, two, sorry, let me clean it a minute. Okay, so here is 0, then here is 0 here, then here is 5, okay? So if I find a trace of it, I'll sum this, right, which is what, 6. Now, from the explanation that we've given in the previous slides, okay, we can determine that easily. We can determine that easily. And what is he saying? Now here, if you look at it, we are summing the eigen what? Values. So when you sum the eigenvalues, it's the same thing as you summing the trace of the diagonal vector. All right. So if you sum the eigenvalues, it's the same as you summing the trace of the uh, So the trace of the matrix. Okay. So the one that you did, the calculation that you did right now, you had the eigenvalue to be 2 and what 4, right? So when we sum this, that is going to be 6. Now, if you calculate the diagonal, okay, if you're able to find a diagonal matrix, when you find any trace of that diagonal matrix, it should also be equal to what? 6. It should be equal to 6. Okay. So this is, the explanation. So A is our matrix equal to, then is the invertible matrix, eigenvector column, eigenvector column. So this matrix here is gotten from the eigenvector. Then this is your diagonal matrix. Then this is the inverse of this P, the inverse of this P. This is your diagonal matrix. Okay. But in this book here, they use this symbol. All right. So the lecture that I use this symbol for that. I didn't use the D. Right. So A can be defined as a product of three matrices. Now, one of the things that we will be doing when you try to multiply vectors, we'll talk about it, you find out that this formula is going to help us to find the product of, sorry, matrices, not vectors, to find the product of matrices. So when I ask you to find the square of a matrix, okay, what are you going to do? You're going to repeat that's this matrix multiplying by itself. Now, if I want to punish you, what I can do is that go on and multiply the cube of the same matrix. If I'm so wicked, I can say, okay, let me give this guy a lot of work where I can say multiply the matrix by itself 5 times. That's going to be a lot of work, right? Now, this is an issue. Computers can do it all right, but those of you who do computer science, remember that in computer science, what we are interested in is what? Computation time. Okay. We want to, spend more resources to do such computation because we don't have, more computation power and also time to do all these things. If you are running this for one day, no, we are wasting energy. So we need to find a way to multiply this quickly, and that is where we'll be using the eigen decomposition. Okay. So let's go. So A can be defined as a product of three matrices. You have the eigenbase P and its inverse. Okay. And these two represent rotation. So the P and its inverse represent the rotation. Then the diagonal matrix represent stretching. So it stretches it. So the diagonal matrix is the one that stretches, where the P, which is from the column of the eigenvector and its inverse, rotates the it causes rotation. Okay, so it's going to cause rotation, while the other one, this one causes stretching, okay, or scaling of the vector. Right. So in simple terms, you are representing a matrix by two rotation and one scaling term. All right. So let's look at this. This is a diagonal matrix. So here, if I ask you to find the trace, you tell me you add this, right? This one to and I also ask you to find the trace, you tell me what you add this, right? And we said that once we can find the eigenvalue and the eigenvector, when we sum this, okay, it's equal to the trace of the diagonal matrix. So we have to learn how to determine the diagonal matrix. And I said that one is gotten from the eigenvalue and the eigenvector. Okay. Now, why are we so interested in diagonal matrix? Diagonal matrix helps us to do computation faster and quickly. You don't struggle a lot. Okay. Now, in real life application, where you have a lot of data set, if you want to do certain calculations or computation, as I said, time complexity will catch you. You don't have the whole day. That is why even my artificial intelligence, deep learning, they are still researching. They want to find out quicker way or better way to train their models. Okay, all these things is you manipulating some of these spaces so that be able to what, do the calculation within the shortest possible time. Because if you have a model that is taking a whole year, to be trained, forget it. No one will fancy that. Okay, so if you want to find or do certain calculations, we prefer to leave our matrices as diagonal matrix so that our calculation can proceed faster and quicker. So let's take this matrix. This is a diagonal matrix because if you look at the diagonal, we only have entry, the rest is zero. Now, for this, we can find the determinant quickly. So if you look at the calculation, you see that if you have a diagonal matrix, this is 2 by 2, you will tell me that if you want to find the determinant, you only multiply what? The entries. That is the answer. So if I have something like this and I give you guys right now, which is 4, 0, then 0, and let's see, 3. Okay. If I ask you to find the determinant, straight away you tell me the answer is what? It's 12. Why? Because it's a diagonal matrix. What do we do? From the formula over here, you just multiply out the diagonal entries and you can get your determinant. This is faster and quicker, right? Yes. So this, you will struggle. If you want to write a script for it, you are gone. Now, what about is 3 by 3? Now, remember the 3 by 3, we use the Laplace expansion to do that, where you remember you have A, then you can have, which is this part. Last time we did that, okay. Uh, let me clean this, then we write it down so that we see that. So we have a matrix A, B, C, D, uh, eh, I'm counting it. Yes, D. Sorry. Okay. So D, E, F, okay, J, H, and I. All right. So if you want me to find it, we said we use the Laplace expansion, and that is the formula we have over here. So it's going to alternate because of the negative one over there. So here we have A here, then we have E, right? Then F, then we have what? H, then I, okay? Then minus, then we have your B, then that one I have D, then F, then J, then I, okay? Then I also have plus C, then I have D, I have E, then I have what? J, then I have what? I. Okay, so this is what I have. All right, so this is when we want to find the determinant, right? Then if you want to find the inverse, you need to find the adjoint and other stuff and be able to find the inverse. But if you can put the matrix in a diagonal, finding this is faster and quicker. Okay, so if we can put this in a diagonal form for us, that means we have is like this. The inverse, as you can see, I mean, we will see it in the slides that will be coming, is much faster and quicker than we going through all this stress, because once you get the determinant, we have to also determine the adjoint before we can even find what? The inverse. Okay, which we need to determine the adjoint before we can find the inverse. But if we can put this in a diagonal, finding the adjoint is all going to happen on the diagonal. Okay, and that is what you can see over here. So if it's a diagonal matrix, finding the adjoint is something that is going to be quick and faster for you. So what do? You just look at how the multiplication is being done over here. You see there's a pattern over here. So if here is A, and here is B, and here is C, you see that where we have the A, we multiply the two columns. I mean the two columns, which is the B and the C over here. Then here, where we have the B, we have the A and the C. Where we have the C, we have what? A and the B. Okay, so once we have this, quickly we can determine what? Our inverse. Okay, we can determine our inverse. Now, if you look at it from all this to determine the inverse, it is just what? The inverse of the diagonal. The inverse of the diagonal. Okay, so if I give you any 3 by 3 matrix, which is a diagonal, then I ask you to find the inverse. So let's assume here I have 2, then 0, then 0, then 0, then I have 1, then 0, then 0, then 0, then I have negative 3. Okay, and I ask you to find the inverse. By looking at what the formula we have over here, you will tell me that say this is very simple. So what I have to do is to what? To find the inverse. So here becomes 1 over 2, then 0, then 0 here, then here is 0, then here too is 1 because 1 over 1 is still 1, then 0, then here too is what? 0, 0, negative 1 over 3. Okay, if we can be put in a diagonal form. Okay, so simply we have replaced each non-zero element with its inverse and we are gone. So you see how the diagonal matrix helps us to be able to do calculation quicker and faster. The same thing applies when you want to multiply matrices. Okay, so I gave you guys an example. If I ask you to multiply two matrices, it's quite easier for you. But if I ask you to multiply the same matrix three times, it becomes tougher. If I ask you to multiply the same matrix four times or five times, you know that you have work to do, right? But diagonal matrix will help us to be able to what? Make it faster. So let's have this matrix. Okay, now if I multiply this matrix by a diagonal matrix, I mean, let's look at it. Okay, we saw from when we started learning about matrix, we said that matrix is not what commutative, right? A B is not equal to what B A, but mind you, when the one of the matrix is a diagonal matrix, it becomes commutative. If one of the matrices is a diagonal matrix, it becomes what? Commutative. So I have a matrix over here. I'm multiplying this one by a diagonal matrix. It's the same thing as when I swap the two, if it's also a diagonal matrix. So when I have diagonal matrix, commutativity in matrix is possible. It is possible provided it's a diagonal, one of them is a diagonal matrix. All right. All right. So once you have the diagonal matrix, when you want to power matrices, so when you have a matrix raised to the power 10 and allows you to multiply this, if I can put my matrix in a diagonal matrix, I'm gone. But mind you, all diagonal matrix should be square matrix. And please, in machine learning, we are dealing with real world data. Real world data, hardly will you find what? A square matrix, right? Hardly. If real world data, they are all in square matrices, thank God. I mean, we can do computation quicker and faster, but hardly will you find real world data as square matrix. Okay, so how do you do that? This is what we're talking about, the singular value decomposition next week. We have to find a way to decompose the matrix so that we can do the calculation quickly. Right. So if you want to power any matrix, we can use what? Diagonalization technique. We try to diagonalize our matrix so that the calculation or can go faster on. And I'm just laughing at you guys that if I ask you to multiply 2 by 2 matrix by itself, that is baby talk, right? But when I give you 2 by 2 matrix and I raise to the power 10, I mean, I can go and bath, sleep, then wake up the following day and you are still working, right? So in machine learning, we deal with a very large matrices and we have to find a way to do the calculation quickly. So how do we do that? We've seen this formula before, right? See, we have a matrix over here, and this matrix we say can be expressed or decomposed as the vector of the the matrix of the eigenvector, then the inverse of this vector, and the diagonal matrix. And this diagonal matrix is coming from the eigenvalues. Okay, so if A is n by n matrix where n is giant, that means a very large number, can be thousand, sorry, 100 or even 50. Okay, how do we do that? Now, this giant matrix can be information about whether any application that you are dealing with, okay, where you've collected data, and I mean, A is large value, okay, that means A is large value. How are you going to do that? So if you want to power A to any t, you can multiply the A by t times, and that is what is seen over here. So if t is equal to 10 and A is large, That means you are going to multiply A by A by A. That is a lot of work for you, right? Yes. And as I said, it's going to take a long time. Even in computation wise, it's going to waste a lot of memory. So we don't want to do that. We have to find a way to solve this. And this is where the diagonalization comes in, where we call it eigen decomposition. So for eigen decomposition, we saw that this can be defined as this, right? You can define as this. So if you ask me to square, then I can repeat it twice. I can repeat that matrix twice. I mean, I can repeat, yes, this formula twice for this because you saw that A is equal to this. So if A squared, that means it's this and that, right? Now, if I put it together, you see that this part is what? I, because it is the inverse times its matrix. So it's going to give you an identity matrix. So I can eliminate that. Then we can simplify this. Now, this is multiplying itself. So we end up getting what? 2. We have simplified this. Now, this is a pattern that if we want to calculate a cube, if you want to calculate a cube, we simply have to, multiply again, and you realize that we have gotten it. So if you look at it, we have gotten a formula. So whatever power that I want to power my matrix, okay, all I have to do is to determine my eigen vector of that matrix and create this matrix, then determine the eigenvalue, then my diagonal. The diagonal is also gotten from, determine the inverse of this, then determine the eigenvalue. And the eigenvalue is what we use to construct the diagonal uh, matrix. All right. So you see how we are trying to, simplify our data, simplify our data till we can do computation so quickly and faster, right? So this formula over here in geometrical interpretation, what are we doing? One, we are doing one rotation followed by stretching, followed by another rotation. So we are rotating, then we rotate, then we stretch, then we rotate. Okay. Now in other books, it's also written like this. In other books, they have uh, the prime, then they also have the inverse, then they will have this, then they also have this. Okay. You see it's in other books, you can also see something like this. They're all correct. Okay. All right, so we stretch, we rotate, we stretch, then what? We rotate again. So we have a matrix over here, all right? So we have this matrix. Now, if you have this matrix, we are transforming this vector by this matrix. And once you do the transformation, this is where we are getting to, okay? So if you guys, let's multiply quickly. So here you get 1, then -5, then -4, then plus your 3, which is 2, then 1, right? So here again -5, then plus your 6, then -4, then plus your 3. So what do you get? You get what? 1, then what? -1, right? So when this matrix takes this vector, it transforms it to this place. Now let's see what we can do with our new formula now. So we said let's rotate, stretch and rotate the vector u with this. Okay, so we are going to rotate it, we stretch it, then rotate it to see whether we'll get to the same place. Okay, whether we'll get to the same place. Why? Because we said this A can be expressed as this. Don't get confused because it's the same thing we are doing. Okay, so A can be written as this. Okay, so if this A is transforming this vector and we are getting this place, that means I can take this expression and also transform it with this vector, okay, with this vector 1, 3, sorry, the vector is 1, 3, vector 1, 3 over here, okay, and I should get to the same place. Okay, 1, negative 1. So let's do it quickly. All right. Now, P is the matrix with eigenvector. Now, we did this calculation already, so we know the eigenvector for this, which it was 1, 1, then half 1, right? If I remember. So, uh, where is this? Let's go back. Okay. Okay, so I want you to do the calculation for me and take your pen and paper. So here the vector is 1, 3. Okay, so 1, 3, we're going to transform it. So we have P, okay, then our diagonal, then P prime, right? Yeah, why am I saying P prime? The inverse. Okay, so this is going to transform our vector 1, 3. And you want to land it on what? 1, negative 1, right? All right, so what do we do? Now we know our P. Okay, P, we know it. And what is the value? It is 1, 1, then 1 over 2. Okay, 1 over 2, 1. I think I'm correct, right? Is this? I think it's this, right? Is it 1? Yeah, 1, 1. Then we can also find the inverse. Now, how do you find the inverse? Please find the inverse for me quickly of this. I'm giving you guys a few minutes. Find the inverse of this. Be quick. Let's hurry up. We are almost finishing. Find the inverse. Find the inverse. Once you finish, you can type it in the chat. Okay. So was it two? Yeah. Okay. Here was 1, 1. Yeah, 1, 1. I wanted to be sure. Okay. So Joshua is saying you are getting the inverse. Okay. Okay, so let's do it together. I think some of them are still no. So let's do it together. So here you find the determinant first, right? So the determinant for this is going to give you 1 over 2 because if you multiply this and you subtract, so you're still going to get 1 over 2. So you have 1 over 2, right? So 1 all divided by 1 over 2. Sorry. Then, I mean, we still maintain it was 1, 1. Then we will negate this, right? We're going to negate this. 1, the negative 1 over 2. This is 2, okay. So here becomes 2. So you end up getting 2 here, then minus 2 there, then get minus 1, then also get 2. This is what you get. 2 minus 2 minus 1, 2. Okay. All right. So this is what you are getting. Yes. I think it's correct. Eh? Yeah, 2. Yes, that is correct. All right. So that is our inverse. So we multiply by the vector and we translate it. Sorry, we rotate it to this place. Okay. So once we done the rotation, then we come to our diagonal matrix. The diagonal matrix, we had our eigenvalue to be -3 and -1. So this is all. So this one is going to stretch it or scale it. So that is the scaling to do a scaling over here. Then once you've done that, then we do the last rotate. We rotate it again. So this is the vector from our, so this is the matrix from our eigenvector. 1, 1, then have 1. Then you will multiply that and this is. So you see, if you should do it, you land on, I mean, the same place as 1, -1. Okay. Okay. So that is that. So this is our matrix we get over here. First, we get to U1. So here we said we are rotating. So we rotate it to this place. Then what again? We scale it to this place. Then now we rotate it to this place. So this will do us that rotation to here. Then once we rotate, we now scale it to this place, then rotate it here. That is the geometric interpretation. Okay, so this process is known as what eigen decomposition, which is a special case of matrix decomposition. Eigen decomposition. Okay. So given a matrix, let me see how many slides that we have. I don't think we have. Okay. So we have some few minutes. Guys, do this calculation for me. So given this matrix, find the eigenvalues and the corresponding eigenvector. Once you determine that, you find the matrix from the eigenvector, you find also the diagonal vector, you also find the inverse of this. Then after that, you find the value of this, then we find the trace. All right, so we have start work. All right, I think 8 minutes will be okay to do all this. So let me set 8 minutes. Be quick. Please participate. Make sure if you don't understand, okay. Now it's better you learn how to do it, okay, so that you yourself, when you see anything like this, be able to ask questions and know what is happening, not just staring at the thing. Okay, all right. So let's be quick. So if you solve any of them, you put it there. Okay, you solve any of them, you put it there. You solve any of them, you put it there. Solve any of them, you put it there. eigenvalue and the eigenvector. Then the rest you can do it later on. Okay. So, all right. So Albert said the lambda one is 2 and 3. Yeah, that is correct. The eigenvector 2 is 1 negative 1, 1 9 minus 2. That is correct. Then the p, okay, so the p becomes 1 1 minus 1 2. That's correct. And the diagonal vector becomes 2 0 0 3. That's correct. And the inverse, yeah, the trace is 5. Yes. So yeah. So Albert's results, please, if you can check Albert's solution. Yeah, you are all correct. Okay. Yeah, the rest of you, yes, you are bringing the answers. That is good. Joshua also, yes. Emmanuel also, yes. Okay, all right. So that is that. So we will build on this next week. We'll build on this because it will be part of matrix decomposition that will lead us into the singular value decomposition. We need to do this calculation so that that one, when we are dealing with the principal component analysis, that will do it next week. We'll be doing this from calculation too as well. And but because we have, libraries in Python that can do this computation fast quickly, we're not going to do it by manually. Okay. So let's conclude it, then we can go. All right. So the only catch is that the matrix that we decompose has to be what? Square. I did explain earlier on. All right. So the only catch is that it has to be what? A square matrix, or else we can't decompose it. All right. So square matrices are hard to come by in real world application. Okay, I said it, I did explain. Okay. All right. So if square matrices are not that common, there's got to be a way to decompose any matricial. This is where singular value decomposition comes in. So you see where we are coming from. So we are decomposing it using the eigen decomposition, and we are saying that if you want to decompose it, it has to be what? A square matrix. But in real life, hardly will you come by any square matrix in your application. So we need to find a different way to do that. This is where singular value decomposition comes in. All right. So, what are some of the application of what we just learned today? So, understanding eigen decomposition is fundamental for grasping several important machine learning algorithms. Now, some of these things you might not, write code for it, but the libraries that are used when they are doing the computation at the back end, some of these things happens. Okay, some of these things happens, and I don't want any of you over here to be at the blind side that what you are doing, as I said, you're just coding, but whatever results that come, then you have to, I mean be able to explain the results, okay, based on your understanding that, okay, this is the result I'm getting. So you think that this is what is happening at the back end, so that we will expect or will be waiting for some of you to tweak some of these existing algorithms to do computations faster and more in a more efficient way too as well. All right. So the PCA relies directly on eigen decomposition of data covariance matrix, and we'll talk about this next week. We talk about this next week. So now that you guys understand the concept of this, we will now use this eigen decomposition in our PCA, which some of you said that is your project that you are going to work on. So next week you will see that. So eigenvectors indicate a direction. We saw it very earlier on that the vector is the one that is talks about the direction, and the value talks about what? The scaling. So if you look at it, it's being repeated over here. So if you're doing your PCA, remember you need to show us some of these things. Okay, so the eigenvector will show us the direction of the maximum variance. Okay, then the eigenvalue will quantify this variance. You see, so one of them is showing the direction of the variance, the other one is going to quantify the variance. You get it? So these are, I mean, the concepts that we need to start applying in our machine learning journey as a data scientists and also machine learning engineers. All right, so 1 minute to 9. Any question, any contribution, any suggestion, the floor is open. You can go on and let me know.